So we're going to do that. All right. 9.3. Look, that corresponds with 18.6. Right? And 10 corresponds with 5. So if I were to ask you, what is the ratio between these two triangles, what would you say?
What, like, the ratio?
Yeah. Of one triangle to another in terms of size.
The second triangle is double in every.
All right, so give me the numbers.
So for angle 7, it doubles in this.
Oh no, I'm not talking not angles yet. I didn't say anything about angles yet. But look, guys. Shh. It is in a 1-to-2 ratio. Do you see it? 1-to-2. 7 times 2, 14. 5 times 2, 10. 9.3 times 2, 18.6. You see, we don't just call that ratio in terms of triangles. We call that a scale factor. Okay, and it has to do with the multiplier from one triangle to another. That's what the ratio means, okay? So, not only are these triangles, do they have the same side lengths, but we see this proportion. This proportional relationship we call scale factor. Question?
Like, when you double each of them sides, but you have to double the, like, measurement of the angle?
That's a great question.
Like the length of the angle.
Time to figure out what happened there. Can I have that one back, Carson? Yes, sir. Thank you. So, Jeffrey asked a great question, right? He's pondering the thought I wanted you all to have, at least a guess. What are the angles going to do? Okay? So we've already proven that, hey, these triangles all, right, you just double the sides. They're all in that same scale factor, that same relationship. So it's time to measure the angles and see what happened there. If I can do that correctly here. So if you look at that one, again, my triangle's not perfect because I did use it by hand, but that looks to be about 31. Don't jump to conclusions. Maybe it's just a coincidence. I don't know. That one's way off. All right, so I didn't draw that very well. But that says, what, 54 degrees? And then this one, it shouldn't be 54. What's supposed to happen here is that they're all supposed to be the same. So I did a poor job in my drawing, I confess. Nonetheless, I hope you see that even though I didn't do a very good job drawing by hand, the mathematical relationship holds up. All right, so that's supposed to be 101. That's supposed to be roughly 50 degrees. Or maybe it's 48 degrees. I don't know. Okay? But look, did I get close enough to prove the point that the angles didn't change?
Yeah.
I mean, like I said, my drawing was imperfect. It totally was. And that's what I was hoping the toothpicks, because they're supposed to be identical, they're probably not even close, would help you see that relationship a little bit easier. Are they very different? Ooh, that one's like a whole 1/8 of an inch different. All right. So, what happened? We doubled all the sides. The angles
Stay the same.
stayed the same. That's because these triangles are, get ready for it, similar. Okay? Similar is not just a vague general word that means close together, alike. It actually has a mathematical context. It means when two triangles are similar, they are proportional to each other, and the angles are congruent. I said it. Should I write it? Nobody else is.
Yeah,
Generally, the teacher writes it when they want you to write it. So, here you go. When two triangles are similar, okay, the angles, in one are congruent to the other. Congruent is the word in math we use for what? Huh? No. The same. Equal. Exactly the same. When two triangles are similar, the angles in one are congruent to the other. As well, the sides are proportional. Okay? So, proportional meaning, look at my scale factor. I have a scale factor. Now, there's a problem set on Delta Math about similar triangles, right?
Yes, it is, and it's low-key confusing.
All right. Well, maybe we can clarify that low-key confusion thing you spoke of. But first, let's make sure we understand the definition. Similar triangles are not just, they look kind of the same. No, they have a particular, specific mathematical relationship where the angles in one are the exact same as the angles in the other, and their sides are all proportionate. Proportionate. I don't know what the right word would be there. I guess we wrote proportional. So, if you have space on the back, or if you'd rather do it in the notebook, maybe we should do it in the notebook. Let's write this out more generally, okay? So, lesson 65. Woo! Similar triangles, okay? So I'm going to use my straight edge here. I'm going to do the best I can. All right, so watch what I do. I'm going to label it. I'm going to do it the best I can. I'm going to call this little a, little b, and little c. I'm going to call this side twice a, twice b, and twice c.
Wouldn't that just be a c squared?
No, because that means a times a, not a times 2. Totally different things. Now, here's the thing I don't want you to think, that it's always twice the size. Okay? It's not always twice the size. It could be 3 times. It could be 10 times. It could be X times. We're going to use a letter. It doesn't matter what letter. We're actually going to use it K times A. K times B. Let's write a B when you say the B. K times C. To indicate that the scale factor is K. K is simply the number by which you multiply the sides in one triangle to get these sides in the other triangle. For our example, it was supposed to be 2 in the lab. Okay, but that is what the scale factor does. The other thing that is preserved, that means maintained, are the angle sizes. So I'm going to do that one in orange. We'll do this one in yeller. This is why colors are helpful. We'll do this one in blue. Bless you. So the angles all maintain the same value. When the triangles are similar. It's not stupid. I don't know what you're talking about, but it's not stupid. All right. So all we find, all we're going to do with this. Wait a minute. You guys ever look at things outside and try to figure out how tall they are? Is that a yes? So, maybe we should do this lab, or maybe I'll just show you the old video. I don't know. But you can actually use this concept of similar triangles to determine how tall something is that you cannot physically measure. Measuring tapes are typically only like 25, 30 feet. What if you wanted to know how tall the tree was because you had to cut it down because you wanted to know how much you should charge to cut it down because you wanted to know how much wood it would produce? That's what your dad does. Yes. So it's sort of relevant, right? What I'm talking about. I don't even know how tall that is. It's about 80 feet. That's not really worth that much. You know, when somebody just like, I'm looking at it. Why don't I always do that voice? They're just like eyeballing. You heard that expression? Eyeballing it. People don't like for you to eyeball their money. So you better get it close to right. So why not instead, we could use something like this. Okay, there's my tree. Beautiful. All right. And it's really tall. Let's say we don't know how tall it is. But it's sunny outside. So it has a shadow. Okay? And the shadow, how long do you want the shadow to be? Okay, too late. 15 feet. All right? What does that have to do with anything, sir? Well, I have actually created a triangle of sorts for us to use. To do something, all right? This is the power of similar triangles. Now, well, how would I be able to measure the 15 feet? Because it's on the ground. You just stick your tape down. You can do that, right? But it's cumbersome, downright dangerous to climb some trees. So you need to know without too much risk, in case you don't get the job. And then let's also say, Mr. Von Cannon standing out here. I have to use him because I'm not 6 feet tall and I want it to be just a simple one. So we know he's 6 feet tall. He's probably 6'1" or something, but we're just going to go with 6 for today. Maybe he's barefoot. Maybe he hurt his back, so he's crouched over a little bit. And then we have that his shadow. Sorry, his shadow's not going to look like a person. I can't. How long should his shadow be? How about we do 2 feet? 2 foot shadow, okay? He's going to love being in my math problem. Do you see the two triangles?
Yeah.
I mean, if I just drew them as triangles instead of like artistic interpretations of a tree and a man, then here's what I've got. I've got some unknown, and this is 15 feet. I've got 6, and I've got 2. This is not to scale, okay? But why am I allowed to say that these are automatically going to be similar? Well, I want you to pay attention to something. That's a right angle. We assume the tree's healthy, just like we assume Mr. Von Cannon is healthily standing up straight. That's a right angle.
You just kind of like a... Yeah.
And then, what is causing the shadow?
Sunlight.
Does the sun hit things at different angles when they're close together?
Yeah. No.
No, it does not. It's called the zenith or the azimuth or something like that. You can look it up. It has to do with the sun angle. All that to say this. That means these angles are going to be exactly the same, okay? Now, logic time.
I ain't got much of that. But...
If these two angles are the same, and both of these have to add up to 180 degrees, guess what? That means this angle up here is the same as this angle. What can you tell me about the triangles now? Yes! Birthday cake. They're similar.
Oh, no.
Wait, why are they similar? Look at what we wrote down. Angles maintain the same value when triangles are similar. If you can prove that two triangles have identical angles between the two of them, then those triangles are able to be proven similar, okay? So, that's cool. What do we get to do with it, though? Well, now we get to use the similar triangles to find out how tall the tree is without even climbing it. Could you see any value in that? You don't actually have to do something to calculate the value.
Yeah, it saves you a lot of time.
And Insurance. Costs a lot of money to climb trees. If you get hurt, somebody's got to pay a lot of money, so you got to pay a lot of money to keep that insurance. All right, here's what we're going to do. See if this looks familiar to you. H over 15 equals 6 over 2. What is it called when you have a fraction set equal to another fraction? Starts with a P, ends with a proportion.
Oh, proportion.
Proportion. Oh, yeah, we said that on the previous page, that the sides maintain proportionality. How do you solve a proportion? This is a previous lesson from like 2 or 3 ago.
Multiply by the reciprocal.
You cross multiply, and you set them equal. So I get 2 times h equals 6 times 15. 2 times h equals 90. This tree is 45 feet tall. All right, now this is middle school mathematics. I don't think that many tree guys use this, especially not experienced ones, because they can look at a tree and kind of tell within 5 feet or so how tall it is. But that's around here. Trees get a lot taller than what you see around you. There's a guy on YouTube who has videos of himself. I think he's retired now, cutting trees he's 200 feet in the air. I'll see if I can find it. But all that to say this, guys. This is what similar triangles are, and this is what we can do with them.